over the course of the next 3 weeks, you will be doing a project that centers on the concept of the conjugates of acids and bases as pairs of molecules that are interrelated in their acid-base properties. And so we've looked at some of these generic reactions in the lecture class already at this point, I'm sure, but in just a refresher sense, we often use HA to represent the weak acid species and A minus to represent the conjugate base of that acid. You could write a pretty similar reaction for a weak base, and we'll do that in just a moment. But the idea is that the weak acid, when it is in a solution of water, it will donate its proton to the water and create H3O plus in solution. And so the pH will be in acidic region, which means it will be below 7 by our typical definitions of what acidic means. The conjugate base, however, if we were just to make a solution out of a salt that contained this conjugate base, which we've called A minus, we would see it react with water in a way where it takes a proton from water and makes actually a hydroxide ion and the conjugate acid of the conjugate base. We can refer to both of these kind of interchangeably. If this is being called the weak base, this is the conjugate acid, and so on. Another way that we're familiar with writing this type of reaction is if you write B for your weak base and your water, and then you have HB with a plus sign and hydroxide. It's really the same thing, and we can write out the conjugate acid dissociation reaction very similarly. I'll write that above. HB plus H2O would produce B and H3O plus. So we can really use these kind of interchangeably how we want to assign our symbols for a weak acid or a weak base. But the general consensus here will be that there is an extra proton on the acid form, and that is not present on the base form. In our base dissociation reaction, even if it's just a solution of the conjugate base of a weak acid, we'll end up getting a basic pH, which would be something by definition higher than 7. And we can use that information to understand something about just how big is the K for that overall reaction. And remember, K is products over reactants. All right, so that means essentially how much conjugate base and weak acid are we generating? Conjugate base and H3O plus, or conjugate acid and hydroxide, depending on which reaction we're looking at. That would be the difference between assigning a Ka or a Kb value. These are just the way that we call them. They're not really that special, but it just has to do with whether we're producing hydronium or hydroxide, whether we call it a Ka or Kb. All right, so now that we've kind of reviewed that, Kw is the water dissociation constant, and it actually is equal to the concentration of hydronium due to the autoprotolysis of water times the concentration of hydroxide. And these two will proportionally shift in solution to always give you that same value for Kw. We can also write this expression as Kw is equal to the Ka, the dissociation of the HA acid and its conjugate base A minus in solution multiplied by one another. So we can use both of these relationships, actually, the hydronium hydroxide relationship and the Ka-Kb relationship to help us solve for the conjugate species in solution, or the conjugate species dissociation constants. We've already seen probably in class that when you want to know the pH, you can take the concentration of the hydronium and you can take the negative log of it to get pH. That p function of taking negative log can also be applied to Kas, to the Kw. So if we wanted to write this same expression of the Kw, but in the P form, we could write pKw is equal to the pH plus the pOH. And then if that is true, then also we can apply that to the Kas, and we could say is equal to the pKa plus the pKb. And since Kw is 1 times 10 to the negative 14, the pKw is 14. So the pH plus pOH will always add up to 14. And the pKa plus pKb will always add up to 14. All right, with that information, we can move on to kind of a sample problem that is similar to what we will do in lab. So let's say you have prepared a weak acid solution at a concentration of 1.20 molar, and you measured the pH. I'm going to put a star because this is a measurement. The pH that you measured was 4.23. Now, of course, there could be error in the actual measurement itself if it wasn't calibrated appropriately, depending on the actual precision of the instrument. But we'll just assume this is a pretty reasonable pH measurement. And we are tasked with using that information to determine the Ka of the weak acid. It's a property of that weak acid. So where we can actually begin is with the information we're given about our measurement, the pH. pH is a measure of the concentration of hydronium in solution. So we can undo that P function, the negative log, we can undo that by taking 10 raised to the negative pH value. And the answer that I got for that for hydronium concentration was 5.89 times 10 to the negative 5. And don't forget that's molarity because it's a concentration. So this value is actually an equilibrium value because you make your solution of HA. Some of this H comes off by reacting with water and makes hydronium. That just happens immediately and you have an equilibrium concentration. So I'm going to actually plug in this value for the equilibrium line of my ice table. So we'll just say it's 5.89 times 10 to the negative 5. If that is true, and every one of those H atoms came from the weak acid, then that must also be the concentration of the conjugate base because it broke apart into those two ions. All right, so that's kind of like a starting point. Now, I've written out the acid dissociation reaction because we know we made a solution of the actual acid. So therefore, it's going to react with water reversibly to make some amount of conjugate base and hydronium. On our initial line, we would write out the concentration that we prepared the weak acid in, which was a 1.20 molar solution. And we'll assume that before it equilibrates, we had no conjugate base and no hydronium in solution. So I put 0 molar for both of those. All right. Now that we've determined based on the pH what the actual concentration at equilibrium is, we could assume that that value is what was subtracted. I'm just going to put like quotation marks to represent, or actually that was what was added, not subtracted. Sorry about that. To represent that. I don't want to write that number again for both of these. So that's what's added, and therefore that was what was subtracted on the reactant side of the equation. However, based on the number of decimal places we have written, aka the number of sig figs we have for our HA concentration, we're not even going to see that difference show up in our number. So I'm just going to write 1.20 molar as our final equilibrium concentration of HA as well. And remember, these are weak acids. Such a small proportion of them is dissociating that it doesn't exactly really cause a change necessarily in your actual weak acid concentration. It's so minute that we won't even see it based on the number of digits we're actually measuring to. Okay, now that our ice table is complete, we can actually proceed to calculating our Ka, because now we have values to plug in for the equilibrium line for each of our substances in the Ka expression. So remember, products over reactants. So essentially I have 5.89 times 10 to the negative fifth. Because that's the same for both A minus and H0 plus, I'll square it and then write 1.20 molar as the concentration for HA on the denominator. And the value that I calculated for my Ka is 2.89 times 10 to the negative 9. All right, this small of a Ka value shows you that this is a pretty weak acid. Now that we've discussed some of the kind of conceptual aspects of what is being covered in this experiment and actually walked through an example problem like what you will have to do in your post lab, I'm going to talk about what's actually going to happen in this experiment. So you'll get to lab, you'll get together with your lab group. You will, as a group, select a pair of conjugate acid-base substances. And there's a table that lays these out for you. And the species that you guys select, you will use for your overall project. So it's important that different groups have different conjugate pairs selected so that over the span of all the different groups, you have a wide range of different species being investigated. All right. Once you've done that as a group, you will kind of look over the guidelines and the protocol again, although you should already have done that before taking your pre-lab quiz. You will plan an experiment based on one of the research questions below. So you'll choose one as well, a research question, to kind of be your guiding problem. And so these questions are: how do the equilibrium constants of acid-base conjugate compounds relate to one another? How does the concentration of a weak acid or base relate to pH? How does concentration of a weak acid or base relate to their equilibrium constants? So all three of these are fair game. Your group can select one. And you will then plan based on kind of information in the protocol, kind of what kind of guidelines are given to you, what data you need to collect in order to answer that research question, and you'll set up your data tables so that you're ready to actually begin the experiment. You'll need to, for instance, calculate what mass to weigh out to prepare your solution from the solid, because everyone will be working with one already prepared solution of one of the conjugates and a solid of the other conjugate. So after that, you will actually carry out your experiment, and that will involve a couple of things. First of all, preparing that solution like we already mentioned, so your stock solution. And then you will use it to make a serial dilution. And this is just a convenient way to vary the concentration of a solution proportionally without having to calculate molar mass and weigh out another sample and dissolve it in a volumetric flask again. With this, you can use a graduated cylinder is not the most precise tool to use for this, but it will work just fine. A serological pipette may be a bit more appropriate, but you'll essentially take 1 milliliter of, this is, if you were making 50 milliliters, you would need to take 5 milliliters, but let's just say you were making 10 milliliters in a 10 milliliter graduated cylinder. You would take 1 milliliter of your 1 molar solution and add 9 milliliters of your DI water, and that would actually take your concentration down from being 1 molar to being 0.1 molar. And you would do this process repeatedly, being careful that you actually, wash out the materials you're using, the equipment you're using to do the serial dilution, because as you get to a lower and lower concentration, any residue will actually throw off your concentration significantly. So it's important to make sure you're using clean, rinsed out equipment for each serial dilution step. All right, so that's just an example, but you'll have to think about how many milliliters you will actually need of each solution to conduct your experiment before actually calculating and doing your dilutions. All right, then after you have prepared all of your solutions, you will measure the pH of these solutions with a calibrated probe, and it's important to note that calibration step so that you can fill in your data tables as you have planned. And the last kind of component of these experiments will be to do a group analysis of your data. And so you're thinking together through what your data means and writing some argument about the research questions. So again, an argument has claim, evidence, and reasoning. So your claim answers your research question, your evidence comes from your experiment and your analysis of your data, and your reasoning incorporates your understanding of the conceptual information as well as how you thought through why that evidence is valid to support your claim.